Okay, so let's get this show on the road. This is 7.4, number 7. So it's partial fraction decomposition. So what I noticed on the bottom here is that the factors in the denominator are linear, and if they're linear, so linear meaning of the form mx plus b. In other words, their roots, what makes them 0, are real numbers. Sorry, not real. They're rational numbers. So what also makes them linear in a sense is that otherwise, so I'll say otherwise, the roots would be there's 2 options, irrational or imaginary. They have an imaginary part to them. So if they're irrational, an example of the first part of being irrational would be, let me not use A and B, let me use 1 and 2. So the first option for them being irrational would be, one of the factors might be something like this, x squared plus 3. Okay, that would be the first case, because then, well, actually even minus 3. So the root would be x equals plus or minus root 3, and that is irrational. So if that's the case, we can't use what I'm about to show you for this one, for linear factors. Okay. All right. Now, the second way that it would not be linear, these are called, by the way, these are called irreducible. So irreducible. So the second way would be if you had something like x squared plus 4 or something like that. So x squared plus 4 equals 0. The roots are x equals plus or minus 2i. And that's imaginary. Okay, so, but these are linear factors. So the way we set them up, the way we set this up is, let me try blue. So I'm going to take that rational expression and I'm going to break it up into three fractions. The first one's going to be the x plus 1. But notice, and then the second one's going to be x plus 1 squared, and the third one's going to be x plus 2. Okay. So here's the thing. If one of your factors repeats, you write it until you write like x plus 1 to the first. It's like, say if it's x plus 1 to the second, to this, like the fifth. It's x plus 1, and then x plus 1 to the second, and then x plus 1 to the third, all the way until you get to the fifth. So x plus 1 to the fifth would have 5 of these fractions. All right. So you put A, B, C here. So you just put A, B, or C for linear factors. This is for linear. It's of this form. A, B, and C are constants. A, B, C are constants. Okay, are y'all following this? Everybody following this? There's a lot of people on the call now.
Just to be clear, you can only use partial fractional decomposition whenever all the denominator is linear.
No, you can use it for nonlinear. You can use it for these cases here. It just looks different. The numerator will be different. It won't just be one constant. It'll be x plus b or something like that.
Okay.
Okay, so we're here. It says imaginary. So we're here, and so what I want to do now is find out what these guys are. Okay. So so what you do is you multiply by the LCD on both sides. Now, Billy asked for this problem, but if any of y'all have questions, stop me. So the LCD is x plus 1 squared times x plus 2. So I'm going to multiply that on both sides. Now, when I do that on the left, x plus 1 squared times x plus 2, like that, they cancel. And so you're just left with x squared plus x plus 1. And when you do it on the right side, so the same thing on the right, certain things cancel according to your rules from intermediate algebra. So you'd get a times x plus 1 times x plus 2, and then plus b times x plus 2, and then plus c times x plus 1 squared. So that would be multiplying what I have in purple there on the right side. X plus 1 squared times x plus 2 over 1, like that. Okay. All right, so we're here. Now, what I do, there's a couple of ways to do this. One way is to multiply it all out and set the coefficients equal. Like you have a polynomial, this is a polynomial, and when you multiply all this would be a polynomial. You could multiply it all out and then set the x squared coefficients equal, the x coefficients equal, and then the constants equal. But that's a lot of work. It's much easier plugging in the roots. So I like to plug in the roots. All right, so I'm going to plug in the roots of the factors on both sides. All right, so here we go. So on the left, let's say on the right, you see that -1 will make that one 0. So I'm going to plug in -1. Both sides. So I get -1 squared minus 1 plus 1 equals, now this one right here, this one's gone, and this one will be gone, because that'll be 0. So we just get the b part. This is b times -1 plus 2. And so what this ends up being 1 equals b. Oh, so b is 1. So right away I know that b on top, that's a 1 on top. All right, so then we plug in -2, because that's another one that makes one of the factors 0. That's a 0 of one of the factors. Plug in -2. So here we go. So on the left we get -2 squared minus 2 plus 1. On the right, this one's gone, and I get c times -2 plus 1 squared. So what is this? 4 minus 1, so that's 3 equals, and then that's 1 squared, so that's c. Oh, so c is 3. All right, so we know that a is b is 1 and c is 3. Okay, and so now I can plug in what a and c are, and then plug in a different number. Now see, what I did just now was I plugged in the roots. Okay, but you can plug in any number into the left and right, and you'll get a true statement. Because when two polynomials are equal, then you can plug in numbers on both sides, and that will be equal. The same number, obviously. Okay, so I'm going to go ahead and see what I'm going to plug in what b and c are, and then I'm going to plug in another number like 0. Okay. So I'm going to take this and this. I'm going to take those and I'm going to plug them into that. So I get x squared plus x plus 1 equals a times x plus 1 times x plus 2 plus x plus 2. B is 1. B is 1. And then c is 3. So that's plus 3 times x plus 1 squared. And I'm not going to multiply to that. I don't need to. There's no point. Okay. So now, once I've done that, I'm going to plug in 0 on both sides. Plug in 0. So I get 0, I get 1 on the left, and I get, plug it in 0 there, it gives me 2a. And then I get plus 2, and then plus 3. So this is 5, put it on the other side, it's negative 4. So negative 4 equals 2a. So a must be negative 2. Just that. So I know some of you are writing this down, that's okay. I'm just going to go through what we just did before we finish this up. I found the factors, and I rewrote them. I did this little piece up here, and then I multiplied by the LCD. And once I multiplied by the LCD, I got this piece here. And then I plugged in factors of the little parentheses one at a time to get B and C out of this. Sometimes you get A, whatever. Once I found B and C, I plug those in to this right there to find A, and I plugged in 0 for X. Now at this point, you could probably, well, no, you'd have to plug in a number. So I plugged in 0 and I got A equals negative 2. So then the fraction becomes, I'll make it bigger in just a second. I just want to write it down. It becomes negative 2 over x plus 1 plus 1 over x plus 1 quantity squared plus 3 over x plus 2. Yeah. And then you solve these individually. So it becomes the integral of this dx. Okay. All right, so I'm going to chill here for 30 seconds and see if you guys have questions. You want me to do anything? Well, did this have limits of integration? 0 to 4. 0 to 4. Any questions at all?
Can you explain to me how C is 3? Like,
Oh, wait, did I screw that up? Oh, no, it's 4 minus 2 is 2 plus 1 is 3. And
oh, you just factored it out.
Yeah.
I didn't see that part. Okay.
I multiplied it up. Yeah. Anybody else? Okay, and then you just solve each one of these. Now, anytime you have the derivative of the denominator as 1, you could use, and the numerator is a constant. The numerator is a constant. You could just pop out natural log for both of those. So this one and this one, those become negative 2 natural log of x plus 1, and then plus 3 natural log of x plus 2. Like that. You can square it, make a cube, whatever. Just leave it like this. It's fine. And then how would you solve this one?
Could you u sub x plus 1?
Yeah, u sub x plus 1. So you let u equal x plus 1, du is dx. And so you get integral 0 to 4. Okay, so this is 0 to 4 still, 0 to 4. And then we get 0 to 4 u to the negative 2 du. So that's negative 1 over u. So it's u to the negative 1 over negative 1, which is negative 1 over u. And then I'm going to go ahead and plug in x plus 1 back in. So it's negative 1 over x plus 1. These limits of integration only apply to x. Okay, so, and now 0 to 4. And then you plug them in. So let's do that. So I have negative 2, we'll use this one, Well, this one over here just becomes -1/5 plus 1. So that one's 4/5. Yeah. These two here, you plug in 4 and you plug in 0. So I have faith you can do that. Let's just do it. 5 plus 3 natural log 6 minus -2 natural log of 1 plus 3 natural log of 2. And the natural log of 1 is 0. This is equal to 0. So you get -2 natural log of 5 plus 3 natural log of 6 minus 3 natural log of 2. You can simplify this, make this all one single natural log, and then you pull the 4/5 over. That's 4/5. There's your answer. Now, I went through that pretty quickly, so if you have a question, ask. Sometimes the hard part is figuring out what integration to do here. Because inverse tangent comes up, natural log comes up a lot, you know, arcsine won't. All right, so the difference with partial fraction decomposition is when you don't have linear factors. Right, so I'm going to leave this problem, so if there's any last questions, please ask. Okay, so what if we had these two factors? Okay, so let me just pick one of them. So an option might be integral of 1/x plus 2 times x squared plus 9, let's say, dx. And you have to split this up using partial fraction decomposition. I don't know any other way to do this. So you would go ahead and write this out on the left, and then on the right, though, you'd have a over x plus 2 plus, and then bx plus c for the x squared plus 9. Because this is the fact the roots are not rational. Okay, they're plus or minus 3i. So they're not real. They're not real and rational. They're imaginary. So this is how you would split it up, and then you do the same process. Now, when you start this, you multiply both sides by x plus 2 times x squared plus 9. Like that. And you're going to get 1 on the left. And on the right, you're going to get a times x squared plus 9 plus bx plus c, bx plus c. I keep messing up. Plus c times x plus 2. Okay, the only root that works, that's real, to do that same process again, right? You start plugging in numbers. X equals -2 is -2. The other roots would be 3i and -3i, and you don't really want to plug that into there. So you plug in the -2, you get something, and then you start plugging in numbers that are not roots, like 0, like we did last time, or 1 or -1, and a, b, and c will come out, no problem. Once again, there's other ways to do this problem, but this is the way I like to do it. And I don't want to, unless you're really confused, I don't really want to show you another way. No, it might confuse you more if you understand it this way. So would you like me to finish this or go on? Anybody?
I'm okay with where it's at.
Can you go back to the previous problem? I wanted to write a few things down. Like towards the bottom, yeah, like right there.
So Billy, did you want to look at it? Did you want me to finish that other problem?
No, I'm okay.
Okay. All right, so I've got Mr. Solis on here, and I've got Jan Fan. Do y'all have questions?
I'm all set.
Okay. Cool.
On the homework, since I mean, I don't know if this is even possible, but is there a way where we can see all of the answers since they're already graded?
Oh, yeah, go into past assignments. and you go in and you can see all the answers. Yeah, I'm pretty sure, right? Jordan, are you done watching? Are you done writing this down?
Yeah, I'm good with that.
Let's look. Let me pull up the student view. You go down and you see past assignments right here. Let me see here. So let's say I want to look at 7.4. Yeah, view key. It's right here. It's at the very top. View key. There you go. So let's click on that. Now, I've had students ask me for an extension request and they've already seen the key. So it tells me if you've seen it. And there are all the answers. And then it shows you the solutions too. That's what's great about buying WebAssign. I mean, yeah, it's a little expensive. It's like 125 bucks or something. But I mean, in my day, the solutions guide in the book alone were more than that. That was like 900 years ago. So, all right, so let's do something else. Y'all are good with the rest of this. What else can we look at? So Billy's asked a question. Who else asked something?
Mine, I have a question about like 7.8. When they're, I think it's comparison.
Right. Yeah, let's look at that. So 7.8, the comparison test.
I don't have a problem in particular. I just, the concept for me.
Yeah, it can be difficult. Let me pick one. Looking on my other screen, and we're going to need this for chapter 11, so it's good that you're asking about it. Okay, I'll pick one. Here we go. There's one arctangent here. Okay, this was number 18. So really what you're looking for is one of these terms that is in between two numbers, because then you can put the whole function in between two numbers and you can compare it to, well, I'll show you. So arctangent is in between, arctangent or inverse tangent, that is in between pi over 2 and negative pi over 2. So I've gone through this before, but it's worth repeating. It's one of the most important functions you'll see in calculus. So this is pi over 2 and negative pi over 2. And it of course, inverse tangents only defined between those two. So that's where it comes from. So then what this means then is, this implies then that if I divide every one of these sides, this side, this side, this side, if I divide it by 2 plus e over x, 2 plus e to the x, I get pi over 2 over 2 plus e to the x. Is less than, it's negative, less than arctangent over 2 plus e to the x is less than pi over 2 over 2 plus e to the x. And that is because 2 plus e to the x is increasing. Since if it were decreasing, it would go the other way around. 2 plus e to the x is increasing. Because that looks like e to the x looks like this. And then when you add 2 to it, just moves it up. This would be at 3 now. 2 plus e to the x. All right, so what we have here is we have a comparison between two functions, this function and this function. So if this one converges, this one will definitely converge. Okay, so let's check it out. Because converging, so an integral converging means that the integral from what to whatever is finite. The answer is finite. And all of these are going to have limits of integration. Okay, so if it's finite, if this one is finite, that area under the curve is finite, then this certainly has to be finite as well, because it's less than. So let's check it out. So, and let's not worry about this 3 right now, that'll come back. All right, so let's try integral pi over 2 over 2 plus e to the x dx. Oh shoot, what happened here? Everything was swimming along great until this happened. Let me see something. How do you suppose we do this problem? Is it U substitution, you think? I think it might be. It might be. I think this one is one of those evil ones. Let me check it out. Ah, yeah, okay, right. So in turn, yeah. Sorry, I'm under the gun here. Also, I would really think about it. In turn, 2 plus e to the x on the bottom. So this is also less than pi over 2 over e to the x, because you're adding 2 there. So it's less than that. So instead of doing this integral, we are going to do this one. So did I throw you all for a loop for doing that? Or do you understand?
What was the thought process behind just dropping the 2?
Well, because here's the deal. When I looked at that, I knew there was something we had to do differently, because when I looked at the previous one, I thought, okay, well, maybe U substitution will work. But when I did 2 plus e to the x is u, then du ends up with an e to the x dx. And there's not another one in there. So I ran into a problem there. And I saw that coming, so I was like, there's something else got to do here. So a lot of times when you're using a comparison test, you can just keep going and see if there's something that in turn is also less than. It's not easy. This is probably one of the harder parts of theoretical calculus, is finding out which you compare it to. Or at least that's what I found in advanced calculus. Okay, so now this is just pi over 2 over integral e to the negative x dx. That is pi over 2 times a negative 1 e to the negative x. And then we evaluate from 0 to infinity. Okay, now once we're evaluating from 0 to infinity, we have to pull in a limit. So that's equal to the limit as t goes to infinity. I can pull out the negative pi over 2 also. And there's a 3. There's a 3 involved. So negative 3 pi over 2. Okay. So now this is e to the negative x from 0 to t. Okay. I replaced the infinity with t. Okay, so now this is negative 3 pi over 2 limit. Now, remember, you can pull out any constant out of the limit. Makes it easier. E to the negative t minus e to the negative 0. Well, this is equal to 1. And this will go down to the negative t going, this goes down to 0. So this ends up being negative 3 pi over 2 times negative 1, because there's a negative on there. Okay, and so this ends up being 3 pi over 2. Okay, now that's not the answer. The answer is it converges, because they're asked, the question was, does it converge or does it diverge? All right, since we got a finite number, that means that this integral converges down to 3 pi over 2, which means that this integral right here would converge as well, because it's less than this one. Okay. Now, I don't know what it converges to, and I don't care. I just know that it's less than 3 pi over 2. All right, Jordan, so you asked for this. Does that make sense?
Yeah, I'm just still writing it down in the
Okay.
process.
I'm going really fast, and I'll send you all the recording. Billy, did you understand it?
For the most part, yes.
Okay.
It's the it's you're taking your function and you're putting it between two numbers.
Yeah.
And then you can find a different integral to solve.
Exactly.
That would be okay. That's
Yeah.
making sense now.
Cool. So you do this also with sine of x. Like you could have a sine of x on top. Sine of x is between 1 and negative 1. And so then you would do negative 1 over 2 plus e to the x is less than sine of x over 2 plus e to the x is less than 1 over e to the 2 plus e to the x. And then you work with that instead. Comes out the same. So this piece here, right here, is how you start. If you can't integrate this one, you keep going. Or you start with something else. You just do something else. All right, Oz. Is it Oz? You go by Oz?
Yeah, I go by Oz.
All right. So you understand this?
For the most part, yes. Just don't get honestly the beginning of it. Just getting the pi over 2. Like I get it's because the function exists in those quadrants. Like I just
Yeah. You just have to know that arctangents between negative pi over 2 and pi over 2. And this is one of the things we went over like one of the first days of class, like in 4.4. I said that this was going to come up over and over and over.
Yeah, that's just my main issue. Remembering all of that. You just gotta brush up on the trig.
Yeah. Like on a test, I'd probably give you sine or cosine. Those between negative 1 and 1, those are easier.
Will there be any comparison theorem problems that aren't with a trig function?
Yeah, there are actually. I mean,
could you look at one of those?
Yeah. There is one that has to do with square roots. And once again, we will see these in chapter 11. So this is not wasted time for sure, because you'll see, because once you're in chapter 11, it's so difficult. It can be difficult that you kind of want to already understand this when we get there.
So what would your advice be to sort of understand this? Because obviously it's good.
Well, here's the thing. What I noticed about this integral when I first looked at it was that you can't do this. I mean, it's just like rough. And I want to get this arctangent out of there because I don't know what the integral of arctangent. I know what the integral of arctangent is, but it's a little bit of a process to get there. And then you're mixing that with this. Okay, So you can't even do them separately. That's not allowed. Can't do numerator and denominator separately. That's not allowed. So I was like, well, I got to look for a function that's between two numbers. And I knew arctangent was, so just worked with that. So you normally learn your that problem there. You learn your trig in your algebra and calculus. Yeah, here we go. I mean, you really learn it. I mean, not that y'all don't know it, but you really learn it well. So this problem, yeah, it's a kind of a mess. Let's see, let's start playing with it. When you have a minus in the bottom, it's not going to help to make this less than anything. It's always going to be greater than. That's just a tip. So let's just start working with the x plus 1 over x to the 4th minus x. Okay, so I know this is greater than x plus 1 over the square root of x to the 4th. I just took away the x. Now, it's going from 1 to infinity. So this x is positive. If it were negative, then I couldn't say this. But since it's always positive, it's getting larger and larger. This one, x to the 4th, is going to stay larger than the x. But whatever we're doing, we're not making this negative, in other words. Okay. All right. You don't really need to know that necessarily. Okay, so now this is equal to the square root of x to the 4th is x squared. This is for x greater than 0. And now this splits up into 1 over x plus 1 over x squared. Okay. So I have the integral that I'm given. Don't worry about the 45 for now. And now it's greater than what I'm going to take the integral of. So let's do those separately. So I'll do the 1 over x in green.
Because you said the x squared.
Well, you can actually use power rule. We're going to use power rule there. Oh, you mean here?
Right.
Yeah, I guess not really, because what's going to happen is you're going to let u equal x squared, and then du is going to be 2x, and you have this extra 1 there. 2x dx, and that extra 1 is going to mess that up.
Okay.
Yeah, good call though. I mean, you try something, it works or not. Okay, so I'm gonna do the one in green first. So integral 1 over x, 1 to infinity, dx. This is natural log. Oh, wait, I got infinity there. So this is limit as t goes to infinity, 1 to t, 1 over x dx. So that's limit as t goes to infinity of natural log of x from 1 to t. Okay, so now plug in t and I plug in 1. So this is equal to limit as t goes to infinity of natural log of t. I don't need the absolute value because t is positive between 1 and infinity. Minus natural log of 1. Natural log of 1 is 0. And what does the whole thing give us? When I plug in infinity into natural log, what do I get?
Is it infinity?
Yeah, it's infinity. And the reason is when you look at the graph, as you go off to infinity, natural log keeps going up. That's infinity. I needed the integral to be finite. The other one was like 3 pi over 2. But the good news is what we found was we found an integral here, which is infinity. Now, I don't care what this one is because now this one's infinity and I'm done, because unless this one also becomes infinity, but it's not. This one's not infinity. Now what's happened is this one does divergent. So this is divergent. The whole thing is because one of them is. And that means that the integral here would also be divergent. So when one that is smaller, see how it's smaller? One that's smaller is divergent, you know, it blows up to infinity. The one that's larger, it's got to be divergent. So graphically speaking, go ahead.
Would you ever run into the case where you would solve for, like say that wasn't divergent, say it converged?
Yeah.
Would that wouldn't make for certain that the other one converged, would it?
Correct. Yeah. Then go the other
So
way.
you'd have to solve for the other side?
You'd have to do something different. Yeah.
Okay.
So let's say that this one here is represented by the red. I don't know, maybe it looks like this. So what it says, this infinity tells us, is that the area underneath that is infinite, all the way to, it's going to infinity. Okay, x values. The other one, so I'll do that one in green, this one. That one is somewhere up here because it's greater than. So the area under that curve has got to be infinity as well, right? It can't be finite. And so the answer is divergent. Now, there are cases where you don't see it in this book, but you'll have infinity here, and then this one will be infinity, and then you got to use a L'Hopital, but that's on a higher level, advanced calculus, but it's a different way to look at it, so don't be confused. It's one of them is infinity, it's divergent. Okay, just know that there's something else going around in the background that we're not looking at today, or this semester. All right. What can I clear up here? Are we good?
I'm good here, but I do have another question I'd like to look at.
Okay. All right, next problem. But nobody has questions.
I don't remember which section in the homework it is, so I'm gonna try and find it, but it's the Simpson rule problems where you're solving for the n.
Oh yeah, we can do that. Yeah, so I'm wondering if there's one in the book that I can pick out, because I think I've done these, done all of them. Let me see, unless somebody had a specific one. See one, see if there's one in the book. So let's see. So what I gave y'all was solving for the n. Okay, so what I gave y'all was number 22 in the book. So let me go to the book real quick. Let me pause the recording. Let me go to the book real quick and see if I can get one that's, okay, so what we're looking at here is, this is number 21 in 7.7. Okay, so we're not going to do Simpson's rule for this. Okay, that's part A, you know. So, but we'll have to do part B because we need to find the K. So it's between 0 and pi. So we're trying to find approximations for 0 to pi of sine of x. Now we can do this directly, but they want us to give us error estimates, and we'll look at S of 10. So S of n, so S of 10, the error associated with S of 10 is less than, I think it's the fourth derivative of x, b minus a to the 5th power over 180 n to the 5th or something like that. I never remember. Let's look at the book. I'm close. It's n and then something else. There's a k. I forgot the k. it's k. This is k. And k has to do with the fourth derivative. 180 into the fourth. All right. So we're looking at the fourth derivative of sine. Okay, so k is less than or equal to the fourth derivative of x on 0 to pi. All right, so I'm sorry, it goes the other way around. F of x is less than k. F to the fourth of x, the fourth derivative is less than or equal to k on 0 to pi. So what we're going to need to do is we're going to find 4 derivatives of sine of x and find out what the max is. Well, it's going to be 1. Oh, this is kind of an uninteresting problem. So I'll do f of x is sine x. You would do this process. F of x is sine x. F prime of x is cosine x. All right, the second derivative is negative sine x. The third derivative is negative cosine x. And then the fourth derivative is positive sine x again. So the maximum of that is 1, because sine goes between 1 and negative 1. So here's your fourth derivative. It's good enough. No, it's not. It's just the sine back, right? And then that is between 1 and negative 1. Those aren't asymptotes. They're just, you know, the maxes and the mins. So this k will be 1 here. All right, so when we put that back in, we get e, the error associated with s of 10. So approximating sine of x, integral of sine of x from 0 to pi. The error associated with doing just 10 subintervals with Simpson's rule is going to be less than or equal to 1 times pi minus 0 to the 5th power over 180 and then 10 to the 4th. Okay, so you get your answer. Okay, let me just do that real quick. Doesn't hurt. So we pi to the 5th. It's pi. Pi, there we go. Pi raised to the 5th power divided by 10,000 and then divided by 180. So the error associated with Simpson's would be 0.00017, and then that's good enough for me. Probably out 8. Okay, now what I'm going to do is I'm going to use the same thing. I'm going to use this to see how many subintervals I need n to get a better approximation. This one, and that is 1, 2, 3, 4 zeros after the decimal place. So question, so part C says how many n needed to get within, to get the integral s of n within 0.12341. So then you put that at there. So I'm going to put that there. So I do k. K is 1, we know that, times pi to the 5th over 180 n to the 4th, and I want to make that basically equal to 0.00001. All right, I'm going to take a breath here. Billy, are you following this?
Shouldn't it be 0.0001? I think you have an extra 0 in there. Maybe not. Oh,
I think
okay.
I'm okay. I think I'm okay.
I was looking at the 0.00017. And that's your, like, your error percentage?
This is the error. The error can't be greater than that for using 10.
Okay.
So error
Oh, okay. Yeah. Okay.
can't
And
be
then now you're solving sort of a different problem where you're looking
Right.
for the n. Okay.
than this if we use 10 subintervals. Okay, now I'm going to see what's better times 10 or whatever this number is. So you just solve, we get pi to the 5th equal 180 times that number. I'm going to cross multiply. I'm cross multiplying. 180 times 0.12341. Wait, I did that wrong. 180 times 0.1234 and then 1. So this is a 0.0018 n to the 4th. I'm a math professor. I should be able to do that in my head, but whatever. Times pi raised to the 5th. I'm trying to get through this. So what I get is 170011 basically. So now take the 4th root of that. And I get 20.3. Okay, I'm glad I did this problem. So I get n equals 20.306. Okay, now I can't have 20.306 intervals, subintervals, okay? So basically what you're doing is you're taking sine of x and you're going from 0 to pi. And you're approximating it, the area under the curve, you're approximating this using subintervals with Simpson's rule, all right? You can't have 20.306 subintervals, okay? So you're gonna round up. When you round up, you get 21, but Simpson's requires an even number of subintervals just because of the way it works. So that needs to be 22. That's how many subintervals you need to get this accuracy. Okay. And the reason you do this, I mean, like we already know the answer to sine, right? Integral from 0 to pi of sine. I think it's 1 or 2, one of those things. They give you a problem that is easy to work with so that you can do harder problems, you know, another time. Okay. All right, I'm gonna let y'all look at that for a second. I'm gonna pause the recording and I'll be right back. I gotta go to the door real quick. All right, we're good? Okay. What else you got for me? What other questions?
I got a question. It's just a integral evaluation, but like here it requires for you to do division. It's the example is integral from 2 to 1 x cubed plus 1 over x squared plus 1.
Okay, you need to do division first. Is that what you just said?
Yeah.
Because the highest power is 3 on top and 2 on the bottom. So you do division.
Because it's the numerator is higher.
Yeah.
Okay.
Yeah. So if degree of the top is greater than the degree of the bottom, numerator, denominator, do long division first. And that's a good catch right there. Otherwise, this is going to be kind of a rough problem. I really wouldn't know what to do with this. So x cubed plus x, subtract, and then we get, oh, what happened here? No, I'm sorry, I'm going backwards. It's x squared plus 1 goes into x cubed. There we go. Multiply it through, you get 1 minus x, and then x squared doesn't go into x. It's negative x plus 1. X squared doesn't go into that, and so your remainder is negative x plus 1 over x squared plus 1. And you do the division. Do you want me to go over how this works again, long division, or you get?
Yes. Yes. Can you go? Can you
Go
go
over it?
over it?
Yeah. So like back in elementary school, when they taught you this, basically if you did like 3 goes into 562 or something like that. You know, 3 goes into 5 2 times, you multiply 1 time. maybe I should go back. 3, 26. This is 8, 24. This is 2, 20. This is 7. This is 21. This is 1. And so you would always write remainder 1. But there's another way to write that. It's actually 187 plus 1/3.
Oh, you just divide it into a fraction.
I divide this number by the divisor, that. So I took the remainder here and I divided it by the divisor, and that was what is left over. It's
Okay.
kind of another way to write the remainder. Okay, so what
Okay.
this, yeah. So in other words, 3 times this would give me 562. So the same idea goes with this here. X squared plus 1 times x plus negative x plus 1 over x squared plus 1 would give me x cubed plus 1. All right, so yeah. Okay, so now this integral becomes the integral from 1 to 2 of x plus negative x plus 1 over x squared plus 1 dx. It just becomes the quotient. The integral of x is easy, and then I would split up this one into 2, one using u substitution and one using, what do y'all think?
Arctan?
Arctangent, exactly, arctangent. So it's the x, and then minus integral 1 to 2 x over x squared plus 1 dx, plus integral 1 to 2 of 1 over x squared plus 1 dx, like that. That's how you finish it out. First one is power rule, easy. Second one, u substitution works with natural log eventually. The third one, arctangent, and then I think you could do the first two easily. When you do the last one with arctangent, so it's arctangent of x from 1 to 2, this ends up being arctangent of 2 minus arctangent of 1. Now, arctangent of a number is an angle. The answer is an angle. It's in radians, but it's an angle. This is an angle, and this is an angle. So what angle, when you take the tangent of it, gives you 1? Tangent of theta equals 1. What's the angle? Anybody?
Pi over 4.
Pi over 4. And then there's not an angle for inverse for 2. So you just rewrite that, inverse tangent of 2, whatever that number is on your calculator. That's the answer to this one. And the other ones are done differently. So Jordan, that answer your question?
Yes.
Okay. I'll let you keep writing.
At that point, it's just straight up. You're just solving it regularly, right?
After that, yeah. And then even if they're the same power, x squared plus 1 over, like the same power, you still divide. So it's greater than or equal to. That helps too. All right. What else you got for me? Oz, don't be shy. You have a problem you want to look at, or Yan Fan? All right.
Yeah, we can just go back to, let's see. So
Which one?
I figured it out. Sometimes I get confused as to when you plug in the infinity at the end, or like evaluating it.
Oh,
And sometimes I don't get that part, but it's actually 12 at section 7.8.
all right. Is it the cube root of something?
Yes.
Cube root of 1 over that. All right, now you have to watch out for these on the test because 0 to 13, I don't know what number you have, but it doesn't matter.
That's the one I have.
What do you have?
That's the one I have.
Okay. What you notice is that if you plug in 13, you get 0 as the denominator. That's bad. So there's an infinite discontinuity there.
Correct.
So we change this to limit as t goes to 13 from the left. 0, there's 13. It's coming in from the left of integral 0 to t. Now let's go ahead and make this 13 minus x to the negative 1/3 power. Right, because if you have cube root of x, this is x to the 1/3. It's in the denominator, so you make it negative. Okay, so, all right, so you can use u substitution here. So u equals 13 minus x. Du is negative dx. So negative du is dx. So I'm going to change this to 1 with u. Just real quick, so it's going to be in a negative u to the negative 1/3 power. And then that would be a negative u, add 1, you get 2/3, divided by 2/3, you're going to get negative 3/2 u to the 2/3 power. Now what I did was I did that off to the side because I don't want to mess with this with u, you know, the letter u. I want to go back to t and x. So this is going to be equal to negative 3/2, and then u was 13 minus x to the 2/3 power. So that is the answer to this. So now this becomes limit, limit as t goes to 13 from the left of the negative 3/2 can come out front. That's this guy. And then it'll be 13 minus x to the 2/3 power, and then 0 to t. Okay, so here we go. So when we plug in 0, we just get 13 to the 2/3 power, which is fine. Let's try to plug in t and see what happens. So it's negative 3/2. Limit as t goes to 13 from the left of, so this is the cube root of 13 minus x squared. Let me write this better. There's a t though. T. And then minus, when I plug in 0, I get 13 to the 2/3 power, cube root of 13 squared. It's inside over outside. Okay, this is finite, so we're good. We're good. We're just trying to see if this converges or not. Okay, so we're okay with that one. As t goes to 13 from the left, this ends up going to 0. So now apply this one. So it's just 0. Because it's not in the denominator, it's okay. Is there a question?
Yeah, that's where I'm confused. Like I evaluate and everything. When I get to plug infinity, it's where I'm like, why does it go to 0? I'm confused with that part.
Well, let's look. So as t goes closer and closer to 13, you get 13 minus 13, which is 0. And then 0 to any power is just 0. The issue before was that it was in the denominator, and we got 0. That's bad. When we did the integration, we put it back in a numerator. There's no numerator here now. It's not like something under that.
Oh, I see. Okay.
You see? So it's just 0, and it's okay. We're cool. So this one's going to be 0, and then we get negative 3/2 times negative cube root of 13 squared. I don't know what that is and I don't care. It's less than infinity. Done. It's minus minus. Yeah, it's positive even. So it's positive 3 cube root of 13 squared over 2. That's less than infinity, so it's convergent. So the integral is convergent. So what we're going to do when we get to chapter 14 or 11 is write functions as polynomials. Any function can be written as an infinite polynomial. And it can only be done if the polynomial that we found is convergent, whatever that means, in the interval that we're looking at. If it's not, then we can't use it. So there's a lot of math coming up. Oz, you okay with this problem?
Yeah, definitely. Thanks.
All right, cool.
I have a question.
Mhm.
Go back to the beginning where you wrote the problem. If there was an x in the numerator and like let's say the power wasn't to the third, like would that mean you would have to solve it like a right triangle?
Yep.
Okay.
Yeah, it would. Well, I would probably put x squared in there and 169 to
Okay.
make it so that it's a nice right triangle. This would be kind of rough.
I think
Now-
like
Yeah, I mean, it would be a right triangle. Let me give you one that you might.
I'm
So-
just kind of like hard because like not like solving the right triangles, but like identifying which methods you need to use sometimes on something like that.
Now, what if I give you this one? Let's do 0 to 1 of the square root of 1 minus x squared dx. So if you plug in 1, you're going to get 0 in the bottom. That's bad.
Yeah.
So what would you do with this one? Is this a triangle problem?
No, because there's no x right in the numerator.
No, it could be a triangle problem. It's just a very hard one. There's a faster way to do it. Does anybody know? It comes from Cal 1.
Is it like a sine or
You're close.
Sine.
What is it?
sine h?
Nope. That would be a plus. Hyperbolic sign. Nope. All right. Y'all write that one down and look it up. You might see it again. So let's go over the 7.3 trig substitution if you want. I think that's what you were talking about. So let me go pick one out that maybe you haven't done before. Let me see what, shoot, did I start this recording? Dang it.
It says recording.
Oh, it does? Okay. All right, good. All right, so let me go back to 7.3. I'll look at the problem numbers and I'll try to pick a problem that is not in the book, that's in the book that I didn't assign. Let's try 13 or 14. Yeah, 13 is good. So this is 13 in the book. 7.3 trig sub. This is the integral square root x squared minus 9 over x cubed. All right, so I see a square root. I see two numbers squared inside of it. Trig sub might work. So let's try it. Make a triangle. If the only way that there's going to be a minus inside the integral is if the square root is here or here. Because Pythagorean theorem requires is c squared minus a squared is equal to b squared or something like that. So in other words, what I'm saying is this: if you have a, b, and c, okay, here's your theta. You have a squared plus b squared is c squared. Let me write it as c squared equals a squared plus b squared. If you pull the a squared over, let's say, it's c squared minus a squared equals b squared. When you take the square root, you get square root of c squared minus a squared equals b. See how the numerator, the hypotenuse was first before the minus sign? That means that x has to be the hypotenuse. When you see that. Anytime, it could be a minus x squared minus x squared. A would have to be the hypotenuse. So for this problem here, we're going to write our triangle so that it's x here. And then we have an option. We can put the square root here, or we can put the square root there. Or in 3. There's going to be a 3. So I'm going to try the 3 here. Put the square root there. This is not right. Let me just show you why. The other option is to switch these. Okay. Now, let me stop right there, because this is a lot of times where I confuse students. I assume they understand how I got this, and they don't. So the idea here is that when you have a squared term and a squared term, you take the square root of each one of those, and those are going to be 2 of the sides. The other side will go according to this little rule that we talked about here. Okay, now this is not the one, because in order to get theta and x together, we have to use a trig function, and the only trig function that'll work for that is cotangent. Cotangent of theta. Tangent is not cotangent, I'm being stupid. Cosecant. Cosecant of theta. Cosecant sine is opposite over hypotenuse, so cosecant is hypotenuse over opposite. That would give me x over 3. And so then I would get x equals 3 cosecant of theta. But the problem is, you can't use cosecant to represent x. And so what we're trying to do is we're trying to replace all the x's and dx's in here with something with a trig function. And you can't use cosecant, cotangent, or cosine to do that. You have to use sine, tangent, or secant to do that. And the only way that you can get x in terms of a trig function, just directly, x equals, is to use cosecant. It's not allowed. So what I'm going to do is I'm going to say, okay, instead, I'm going to switch the 2 sides. I'm going to switch these 2 guys. This doesn't work. So, and Jordan, I think this is what you're talking about. It's like, where do you put what?
Yeah.
That's the idea. So now when I try it, I'm going to use secant of theta. Secant is 1 over cosine. Cosine is adjacent over hypotenuse. So secant is hypotenuse over adjacent. So it's x over 3. 3 secant x. 3 secant theta is x. Ah, there we go. This is my triangle. Then you work from there.
You're trying to find, in order to establish what goes where on the triangle, you're just trying to find what x can equal.
Yeah.
Okay.
Exactly. So if it were x squared plus 9, all right, so then you finish it from here, right? It ends up being secants and tangents. So let's look at another one that's similar. So like what I would do is I would give you that in the homework, but on a test, I'd give you integral square root x squared plus 9 over x cubed dx. Now it's a different triangle because there's a plus. And the only way there can be a plus is if that square root is on the hypotenuse.
Yeah, because of tangent, right?
Yeah. So this one would be square root x squared plus 9. The x goes here, the 3 goes there for tangent. So tangent of theta is x over 3. 3 tangent theta is x. Now, there's no problem in you picking the wrong sides. So say you picked this instead. Square root x squared plus 9 3 and x. Here's theta. Well, the only way to get, so you do your tangent. Tangent theta is 3 over x. X tangent theta is 3. Well, now that x is divided by tangent, x is 3 cotangent. 1 over tangent is cotangent. Well, that's not allowed. Use secant, sine, or tangent. If you use the other 3, you end up with a negative in the integral. So I have yet to see a proof of that, actually. So, all right. So that's how you do that.
Okay, yeah, that helped.
Okay. 9 minus x squared. Okay, let's do that one. So integral square root 9 minus x squared over x cubed dx. Okay, now the only way for the square root to have a minus is if it's one of the sides. So it can go here or here. Let's just try it on the bottom. So what would the numerator, what would the, I keep saying numerator, hypotenuse be? So you take the square root of each one. That's going to be the other 2 sides.
X, right?
No, 3. Because in order to get the first term, when you have a minus, the first term, that's going to indicate what the hypotenuse is going to be when there's a minus. Because of how a squared, b squared, and c squared work. Just go back up to that. A, B, C. C squared is a squared plus b squared. Move one of them over. Take the square root of both sides. Notice that c comes first with a minus inside, so c's got to be the x. In other words, 3 has to be the hypotenuse.
Okay.
All right. So that's how you set that one up. And here, let's double check. So sine of theta is, I'm looking at the blue, x over 3. So 3 sine theta is x. Yeah, there we go. Got it. And you keep going. All right. No one said this class was easy. I'm not saying you think it does. It should be. I'm just saying I'm even seeing myself that this is pretty darn hard because it's so much to keep up with.
Yeah.
Imagine taking a midterm. So I used to give midterms, and you'd have a midterm Tuesday. That includes all of chapter 6 as well. Volumes of revolution, all that stuff. In fact, I normally put a volume of revolution on this test.
Will there be one?
Let's just say I'm being a little nicer this semester.
Yeah. So then.
All right. You should know how to do it though. At least for the fun.
Okay, so that means, does that mean the x squared plus a squared, it'll always be the variable as the hypotenuse then? It'll be the exact opposite?
Yeah. It's a squared minus x squared, then the a is going to be the hypotenuse.
And then x squared minus a squared is the x is in the hypotenuse.
Exactly.
Okay. Yeah. Okay.
Yeah. All right.
And tangent can work either way, you said?
No. Tangent.
No.
Well, no. The x has to be here for tangent.
X has to be, okay.
So the only time the x is at the horizontal leg is with secant. It's when it's x squared minus the number. It's that then the x is in the horizontal leg. All right, what else we got? We got a few more minutes.
That's all I have personally.
Anybody else? So let me pause this.